Section 5 from Unit 2 discusses atomic numerals and introduces the periodic table. If you haven't already downloaded one onto your iPad or have one pulled up on a browser somewhere, go ahead and do that so you have quick access to it. The first number we need to talk about is called the atomic number. This is often represented by the capital letter Z, okay, maybe not here in your box of your particular element, but outside of that you'll see it as a capital Z in equations or formulas or symbols. So atomic number. This is the number of protons in an atom, and the number of protons in an atom identifies it as an atom of a particular element. Okay, so if you look at the top left box of the periodic table, you'll see hydrogen, all right, and you'll see a big number hopefully somewhere on your copy of the periodic table. That tells you how many protons hydrogen has. Okay, hydrogen's the first element. It has 1 proton. Okay, so it's the very, very first element. It's the lightest element. It's only got a single proton. If you have 0 protons, then we're not talking about an element, right? It can't possibly exist as an atom that way. Okay, so the atomic number is the big whole number there, and they go in order on your periodic table. The number of protons in an atom is its atomic number. Okay, we just said that. In a periodic table, this is generally indicated across the top of every box or in the middle. It's the biggest whole number around there. If an atom is neutral, which we are assuming for at least right now, we're assuming neutral atoms. If there is 1 proton, that means hydrogen has 1 positive charge in the center of it. That means it needs 1 negative charge to balance that out. Otherwise, it's not electrically neutral. So in neutral atoms, we have equal numbers of protons and electrons. So hydrogen has 1 proton. It will also have 1 electron, assuming it's neutral. Okay, so I'm going to fill in the first line of this, and then I want you to fill in the last 2 and just see how you do here, okay? So if it gives us the element symbol as Pb, by the way, that's lead, and the atomic number of 82. So if you find Pb on the table, it'll tell you the atomic number is 82. For now, let's assume that all of these atoms are neutral, and if you don't have that periodic table downloaded or pulled up on a browser, go ahead and do that. But if we have an atomic number of 82, that means we also have 82 protons. And assuming that it's electrically neutral, if I have 82 positive charges, I better have 82 negative charges, okay? The second one here tells us we have 8 protons, so see if you can fill in the rest of this line. And the last one here tells us we have 30 electrons, so fill in that line as well. Okay, so with your periodic table, I want you to find radon and magnesium and tell me how many protons each of those have. Okay, you should have come up with 86 and 12 as the answer there. Okay, this one says a neutral atom of an element contains 66 electrons. Which element is it? Figure that one out. Okay, that should be element 66, which is dysprosium, dy. An atom of an element contains 14 protons. Which element is it? You should get silicon there with that one. And then down below, do the figures have the same atomic number? So look at what's in them and see if they are. And you should have yes, because they both have 9 protons. So Dalton's theory in 1803 was incredibly helpful in pushing forward chemistry as a science, but it was wrong about 2 things. It was wrong that atoms were indivisible. Okay, we later figured out you can split atoms, right? We figured out how to create atomic bombs, hydrogen bombs. But he was also wrong about all atoms of an element are identical in mass. That is not true. Atoms of an element can have different masses. The atomic number must be the same. The number of protons must be the same. The number of neutrons, though, doesn't have to be. Okay? For an atom to be neutral, we have to have equal numbers of protons and electrons. So we can always maintain that. That's not too hard to do as long as we have equal positive and negative charge. But the number of neutrons, it doesn't add anything to the charge, right? All it does is add mass. So neutrons do not affect an atom's charge. Therefore, the number of neutrons in an atom can vary. Now, sometimes there's only one option for the number of neutrons. Sometimes there's multiple options for the numbers of neutrons in the same element. Okay, so for instance, we can have an oxygen atom that has a atomic number of 8, right, 8 protons, but has 16 as its, what we'll call the atomic mass, 16 protons plus neutrons. So it's got 8 protons plus 8 neutrons. We can have an oxygen atom that has 17 as its atomic mass, which means it's got 8 protons plus 9 neutrons. Okay, so we can have all kinds of setups here existing with different numbers of neutrons. And we're going to see what this looks like. Okay, so Another example here is potassium. Potassium's atomic number is 19, meaning it has 19 protons no matter what. If you change the proton number, you've changed the element, so that can't possibly change. So it's got 19 protons. Since it's electrically neutral for what we are assuming, it must also have 19 electrons. Okay, so what about the numbers of neutrons? There exist 3 different types of potassium atoms. There's potassium with 20 neutrons, there's a potassium that has 21 neutrons, and there's a potassium that has 22 neutrons. Okay, so there are 3 different versions of potassium. All right, they all have 19 protons, they all have 19 electrons, but the number of neutrons here does change. Atoms with the same number of protons and electrons, but different numbers of neutrons are called isotopes. Okay, isotopes. So we can have different numbers of neutrons within the same element. Now, if we have more neutrons, we have a larger mass, obviously, right? The more neutrons we have, the greater that atom's going to weigh. The next question is, do isotopes affect chemical behavior? Does it make it behave differently? And that answer is no. Okay, so all 3 of those versions of potassium that had 20 neutrons, 21 neutrons, and 22 neutrons, they all behave like potassium. They don't change, okay? Their mass is slightly different, all right? The 22 is slightly heavier than 21, which is slightly heavier than the 20 version of it. Okay. Now we need to introduce something called isotope notation. Isotopes are identified by their mass number, and I was saying this just a minute ago, but mass number is equal to the number of protons plus the number of neutrons, which you can really think of it as number of particles in the nucleus. Okay? Total number of particles in the nucleus, right? Protons plus neutrons is what this is. And how we say these things, okay, is we say copper 63 is verbally how we say this, or how we write it out like this. Now there's an isotope notation, which you'll see on the next slide, which we'll talk about. But you'll read these as copper 63, okay, or copper 65. What that means is that this version of copper has 63 as its mass number, and this version of copper has 65 as its mass number. So this example here, let's make sure this is a 0. Copper 63, if you find copper on the periodic table, okay, it's element 29, it has a symbol Cu. It has 29 protons. It's element number 29. So if copper 63, this version of it, has 63 as a mass number, and that's the protons plus the neutrons, you could figure out how many neutrons are in this thing simply by taking 63 minus 29. Okay, let's make sure we get this right. 63 minus 29 is 34. So there would be 34 neutrons in copper 63. I want you to figure out how many neutrons would be in copper 65. Remember, copper's proton number cannot change. So how many neutrons does copper 65 have? Okay, how many does that one have? So when we type it out, we'd write, copper 63, like you saw on the previous slide. But what you will often see is this written in what's called isotope notation. Okay, and here's your generic formula over here, right? This is the box you want to pay attention to over here on the right side of the screen. Okay, it's written like this, where A is the atomic mass, Z is the atomic number, right? We saw that before, and X is the symbol. So X is the atomic symbol, A is atomic mass, Z is atomic number. Okay, so practice writing copper 63 as an isotope notation. We'd put the Cu. The top number out front is the protons plus neutrons, right? That's what this is. This is protons plus neutrons. And then this one down here is simply just the proton number, okay? Oftentimes what you will see is you won't see this thing written like this. What you will see is just 63 Cu. And the reason is that this 29 is assumed. In order for this to be copper, it must have 29 protons. So sometimes they will not put that 29 there because if you have a periodic table, you know this information. You don't necessarily know how many neutrons are in that atom, though. Okay, so that would have to be given to you or some way or another to indicate the protons plus neutrons of this particular isotope. All right, and the one over here, right, if writing without the 29 would be 69 C or 65 Cu, like that. Okay, so that's what isotope notation looks like. Okay, so we're going to practice writing a few of these out just so that you get used to it. So this first one here, neon, and it's got a mass number of 22. Okay, I'm going to write them right here next to it. So the symbol for neon, it's element 10 from the atomic number. So it's got 22 as its mass number, so we could just write 22 Ne. If we wanted to, we could put the 10 down there, but we don't have to because neon must have 10 protons. Okay. Real quickly, just off to the side here, the number of neutrons in this particular thing would have to be 12, right? 10 plus 12 would get us to 22. Okay, so calcium, symbol is Ca. The mass number is 46. If we want, we can include the 20 as the atomic number, but again, it's assumed, so we don't have to write that. And then the number of neutrons here would be 26. Okay, we'll do one more, and then I'll have you guys do a couple of these for practice. So oxygen, it's got atomic number of 8, mass number of 17, so we've got O with a 17 over the 8. Again, we don't have to write the 8, we have to write the top number. And then number of neutrons in that particular one would be 9. So try these last three here. An important thing to know is that each isotope of an element doesn't exist in equal quantities. The abundance of each isotope varies. Okay, we call this relative abundance or fractional abundance is what you'll also hear. So relative abundance is constant anywhere on Earth, though. So going back to that potassium, we had potassium that had 20 neutrons, potassium that had 21 neutrons, and potassium that had 22 neutrons. And so the mass numbers there would be 39, 40, and 41. All right. They don't exist in a 1/3, 1/3, 1/3 split. 93.26% of potassium is potassium 39, 6.73% of it is potassium 40, and 0.01% of it is potassium 41. Okay, so again, it's not 33.33, 33.33, 33.33. This distribution, okay, is like this, and it's like this everywhere on Earth. All right, to the best of our knowledge, that is the distribution of it. And what that means is that when you're finding the mass of a potassium, a sample of potassium, you have to keep in mind that not all potassiums weigh the same amount, and that some of them are slightly heavier than others, and that they exist in different ratios, not just however many different isotopes there are, right, under one. So we got to find these percentages. That also affects the mass of this element, the average mass of potassium. Okay, so if you remember from the very last slide of the previous lesson, if you saw the masses of subatomic particles, you saw how incredibly light they were. 10 to the negative, 28th, 10 to the negative 31st. Those things are incredibly light. So rather than dealing with extreme scientific notation all the time, scientists created a new unit to express mass when we're talking about atoms, and that unit is AMU, which stands for atomic mass unit. Okay, so masses of subatomic particles are so small that a new unit was created. Chemists use carbon-12 as the standard. So carbon-12 has 6 protons, 6 neutrons, and 6 electrons. It's got 6 of each. So they took the mass of that and divided it by 12. So 1 AMU is 1/12 the mass of a carbon-12 atom, and that's how we get these numbers here. So you can see relative values here. Electrons is still about 1/2000th that of a proton. All right. This is what we're going to use to determine the actual masses of atoms. Okay, we weigh them out in AMUs. So you've probably noticed if you look on those boxes of the periodic table, there are numbers there that have got a lot of decimals to it. Okay. So if atoms have whole number masses in AMUs, why does the periodic table show the mass as a decimal? And that's because isotopes have different masses and their abundances are different. They don't exist in perfect splits, a 50-50 split. They exist in percentages, right? A random percentage. So that's why if we look at something like chlorine, for instance, there's chlorine 35 and there's chlorine 37. But if you go look at chlorine on the periodic table right now and find this, it'll say the average mass of a chlorine atom is 35.453. And that unit would be AMUs, even if it's not listed there. So what that means is that this right here is an average of these two, but notice it's not 35 plus 37 divided by 2. It's 35 times this percentage and 37 times this percentage added together, and that's how we get this number. So we're going to figure out how do they calculate all of these numbers on the periodic table that are the average masses of an element. Okay, and we're going to do that with chlorine. So we had chlorine 35. We have an atomic mass. If we add up all the pieces of chlorine, the 17 protons, the 18 neutrons, and the 17 electrons, and we add all those up, we get an atomic mass of 34.969 AMUs, and the fractional abundance is 75.78%. Chlorine 37 has an atomic mass of 36.966 and a fractional abundance of 24.22%. What we are going to use is this equation right here, and make sure you get this down. And I know it looks scary because there's some stuff in here you haven't seen before, at least one thing you haven't seen before, but it's really not too bad once you get used to this. Okay, so AAM stands for average atomic mass. All right, average atomic mass. This symbol here, it's the Greek letter sigma, okay, is what that is. And it means the sum of, all right? That's what that means. So the average atomic mass is the sum of all the atomic masses times the fractional abundance as a decimal. Okay, so if you have 2 atomic masses, okay, of the isotopes, you got 2 isotopes, means that we're going to have 2 setups that we're going to add together. All right, so we'll show you how to do this. If we have 3, isotopes, we'd have 3 setups. If we had 4 isotopes, we'd have 4 setups, and we just add them all together. It's really not too bad. So we'll do this one with chlorine, and then we'll have you guys do a practice one here at the end. So the setup here, the average atomic mass, that's what we're solving for. Now, we know the answer because the answer is on the periodic table. All right, it was 35.453, I think, if I remember correctly from the previous slide here. But let's go ahead and do this. So the sum of the first one, chlorine 35, has an atomic mass of 34.969 AMUs. And we're going to multiply that times its fractional abundance as a decimal. So we need to divide that by 100. So we're going to multiply that times 0.7578, okay? And that's the first one. Then we need to do it again for the second one. The mass of the second one is 36.966 AMUs. And we're going to multiply that times its abundance written as a decimal, 0.2422. Okay, and then we're simply just going to do the math and add all of this up. 34.969 times 0.7578 plus 36.966 times 0.2422. All right, and if we write all of this out, we get 35.45. I'll just write all the numbers down. Okay, obviously we would need to round this off using significant figures. Okay, if we use 4 digits because that's the most we've got there. We end up with the number, right, 35.45, and I know we rounded that to a 3 on the previous page. So 35.45 AMUs. So turns out this math works out. Notice we didn't just take this plus this divided by 2. Okay, we don't do that to find the average. We have to multiply times its fractional abundance. Okay. So atomic mass does not always indicate the isotopes that exist. You have to be careful with this. So for instance, if you look at fluorine on the periodic table, 100% of natural fluorine is fluorine 19. There is only one isotope of fluorine. That's it. It only comes in one variety naturally. You can try to make other ones, but they'd be radioactive. Naturally, there's only fluorine 19. That's it. But if you look at something like bromine, for instance, this is why you have to be careful. Bromine 79 is 50.69%, and bromine 81 is 49.31%. Bromine 80 doesn't exist, at least not naturally. There's not an isotope with 80 as its mass number. Even though if you go look at the average atomic mass on the periodic table, it'll say it's 79.904. So that leads you to think, well, wouldn't there be bromine 80? No, there's 79, there's 81. Which average out to be this 79.904 with these 2 percentages, but there is no bromine 80, so do be careful with that. Okay, so here is a sample problem for you to try, and I would say now just round your answer, just for the sake of making it easy, round your answer to the nearest 0.01 AMU.